Okay, so good morning, everybody. Welcome to the 51st lecture. Though I guess for MSc this is not that. It's I don't know, the 21st lecture or something like that. So we have been talking about angular momentum, and so what I've discussed so far is the commutation relations of angular momentum, and the fact that if you want a complete set of commuting operators, then you need to include L square, the square of the total angular momentum. And then we need to define certain ladder operators. And exactly in analogy with the harmonic oscillators, these ladder operators. So if you look at the commutation relation with if you look at the harmonic oscillator, for example, you have A dagger and A. Here you have L plus and L minus. And 1 second, you just should warm. Fan speed increase. Okay. So and these operators, then we can so L plus and L minus are like A dagger and A, and the number operator is like LZ, right? So if you look at the effect that A dagger has on the number operator, it increases the eigenvalue by 1. Similarly, if you look at the effect that LZ at L plus has on, if you look at L plus, what it does to an eigenstate of LZ, it increases that eigenvalue by H bar. Okay, so the key to understanding this is to understand the commutation relation of LZ and L plus. Okay. And this is true in general, right? If you have any, let's say, two operators such that you have A, comma B is equal to plus or minus B, right? Then the same algebra tells you that if you take B and act on an eigenstate of A, what you will get is another eigenstate of A with plus or minus 1. So in this case, 1, because there is no factor of H bar over here, multiplied by B eigenvalue of A. Okay. So this is very, this is something that is useful to remember, that whenever you have this property, this commutation relation, then B is going to increase or decrease the eigenstates of A by 1 unit. And then what about L square? Well, L square commutes with L plus minus. So we can label any eigenstate with two eigenvalues. One is the eigenvalue of the total angular momentum, and the other is the LZ eigenvalue, right? And now, as I explained in yesterday's class, it is natural to expect that LZ square, which is the projection of the Z projection of the total angular momentum, right? So that is one component of L square, right? And it is natural to expect that that component, the maximum value of that component cannot be larger than L, and the minimum value cannot be smaller than minus L, right? So that gives us some restrictions on the possible maximum and minimum eigenvalues of LZ square. And to understand what that restriction should be, we look at this quantity L square minus Lz square. Okay. And then we can expand both of all of these terms. So L square minus Lz square can be written as Lx square plus Ly square. Lx and Ly can be written in terms of L plus and L minus. And L plus and L minus are Hermitian conjugates of each other. So L square minus Lz square can be written as something like this. So when you take so it is like writing A dagger. So if you take the expectation value of A dagger, right? So A dagger is a Hermitian operator, right? And if you take the expectation value of A dagger, you will get something. Well, it's not only a Hermitian operator, but it's also a positive operator, right? So if you take the expectation value of A dagger, this is always going to be greater than or equal to 0, because this part is simply the Hermitian adjoint of this state. So I'm writing A dagger psi as the state phi, and so bra psi times A is the bra phi, right? So the inner product of phi is always greater than or equal to 0. So we use this property and we find that, well, L square minus Lz square is always greater than or equal to 0. Again, we expect this to be the case. This should be the case because as we explained, Lz is a component of L, right? Then we want to look at we want to understand, well, what are the restrictions apart from this? I mean, okay, it's fine. So now we know that there is some maximum value of Lz, let's call that M max, and such that, so what is the effect of L plus? L plus always increases the eigenvalue by 1, right? But you cannot increase the value of Lz beyond a certain point, right? Because the component of the vector can never be longer than the size of the vector itself, right? So that means when Lz reaches the maximum eigenvalue, at that point, action of L plus on that state will give us just the 0 state, nothing. It annihilates that state, right? And so then L minus acting on this whole thing will be 0. And then again, doing some algebra, we can write down that we can relate A, which is the eigenvalue of L square, to this M max, right? Are there any questions at this point? Please ask me if you have any questions. As I've emphasized in the previous class, angular momentum is a very, very central part of quantum mechanics. And it is very important that you master the techniques over here, okay? So, all right, so that's why I'm going a little bit, I'm being a little bit repetitive, and online class 51, December 18, and angular momentum continues, right? So what do we have now? We know that the eigenvalue of, so L square, we'll write AM is equal to A M. So this A is the eigenvalue of L square. And what we have found is that this A is equal to M max into m max plus h bar, right? And now we can perform the same kind of logic only with L minus. So we know that L minus, it takes this eigenstate and sends it to m minus 1, right? Now again, that tells us, so because the LZ can never, if you look at the absolute value of LZ, just the classical LZ, not the operator, right? This always has to be less than or equal to the magnitude of the vector L, right? Right. So that tells you that LZ max is what? It can only be plus magnitude of L, and LZ minimum, right? So again, we know that there should be some, so when you decrease the eigenvalue, you will reach a state such that this M is minimized. And when it is minimized, what will happen? You will find that L minus acting on the state is 0. So I just want to make sure that everybody follows these arguments. If you don't follow these arguments, please tell me so I can explain or go over any doubts that you might have. And if you have any questions, you can ask at any point in time. So is this clear to everybody? I mean, of course, you have to sit down and do your homework, which is to go through these derivations on your own. So then again, we follow the same logic that L plus acting on this state will be 0. And then L plus minus, we can write as Lx plus I Ly. It's the same thing, exact same thing as we did in the previous case. That L minus L plus is this. So L will be exactly the same thing, Lx square plus Ly square. But now this will be positive. That's the only difference. You will get plus h bar Lz. And this can be written as L square minus Lz square. Lx square plus Ly square can be written as this, plus h bar Lz. So L square minus Lz square plus h bar Lz acting on A is equal to 0. Right? So L square acting on this state will give you the eigenvalue A. Lz acting on this will give you the eigenvalue Mn squared plus h bar Mn Mmin is equal to 0. Right? And again, and so you see that A is going to be equal to Mn into Mn minus h bar. Okay. So now we have two such relations. We have this expression. This expression relates the maximum eigenvalue of Lz to A, and this relates the minimum eigenvalue of Lz to A. And you have to keep in mind that through this whole process, L stays fixed. We are not changing A. Sorry, A stays fixed. So A is the eigenvalue of L square, right? So the total magnitude of the vector is not changing, right?
Yes, sir.
Okay. And so these two are equal to each other, and that tells us that what does that tell us? That tells us that mn minus h bar is equal to m max plus h bar, right? And if you ask what is the solution of this, well, you can, one solution that you can check is that m max has to be equal to negative of m, right? So if you substitute minus mn over here, you will get the same expression. So that means that all of the eigenvalues of Lz lie between, let's call this B, they lie between plus B and minus B. Okay. But now we know, so that means what is the lowest eigenstate of Lz? It's A comma minus B. What is the highest eigenstate? It's A comma plus B. And now we know that if you want to go from this state to this state, well, what do? You take L plus and act on this. And what do you get? You get some constant which we have, we haven't worked that out. We'll see what that is. Minus B plus H bar, right? So if you keep repeating this process, if you keep acting with L plus, you get minus B plus H bar. Again L plus, you get minus B plus 2H bar. Until you get to A prime minus B plus. Now, after acting on it n times, you would get minus B plus NH, right? Because at each step you get one copy of H bar. And so this means that the maximum value of B, which is plus B, has to be equal to minus B plus NH bar. Right? From this, we can see that 2B is equal to NH bar, or B is equal to NH bar by 2. So what is this? What is B again? This B is the maximum eigenvalue of Lz. And what we find is that this maximum eigenvalue of Lz has to be some half integer multiple of H bar by 2. And so what is n? N is equal to 0, 1, 2, so on. Okay. From this expression, now we can read off what the allowed values of A are. And what is A? A is the eigenvalue of L square. So A is equal to M max into M max plus H bar, which I can write as B times B plus H bar. So if I substitute this expression, I get N H bar by 2 times N H bar by 2 plus H bar. Pulling out all the factors of H bars, I get H bar square into N by 2 into N by 2 plus 1. So A takes this form. Okay, so again, purely by using the commutation relations, we have found that the eigenvalues of A, of L square and Lz are quantized, and we can determine the entire spectrum of these eigenvalues simply by looking at the commutation relations, and also using a little bit of physical reasoning. And now we write n by 2 as j, and so A is written as h square times j into j plus 1. And this is the reason that when I write A comma M, that's also that's the same as saying j comma M. So A is the eigenvalue of L square, but the eigenvalues of L square are also, you can also label it by j, right? Because these two are related. So this is the eigenstate of angular momentum. When I act on this eigenstate with L square, I get the eigenvalue A. I get h square into j times j plus 1, j comma M. When I act on it with Lz, I get M times j comma M. What are the allowed values of this? So what is the maximum value of M? The maximum value of M is B, and B is equal to H bar times J. So I can write B, which is M max, as J times H bar. Okay, so what is the maximum value of M? It is plus JH bar, and the minimum value is minus JH bar. So I can label the eigenstates like this: minus J, minus J plus 1. I have dropped the factor of H bar, okay? So on till J comma J minus 1, J comma J. These are the eigenstates of the angular momentum operator. Any questions at this point? Any questions on YouTube? Yeah. Again, on YouTube, if people have any questions, please ask me, okay? So this is actually a very beautiful result, right? I mean, again, we have not used any differential equations, nothing. It is just pure commutator algebra. That's it. And now we can ask, what do these numbers look like? What does the spectrum look like? So we know that J is equal to n by 2, where n can be, let's say, 0, 1, 2, and so on. So if for n is equal to 0, let's see, for n is equal to 0, what are the possibilities? We get J is equal to 0. What about m? M is also can only be 0. That's it. This is the only state, zero angular momentum state, right? This is also referred to as an S wave, right? So you have the S orbital, right, of a hydrogen atom, for instance, or any other atom. That S atom has zero angular momentum, right? For n is equal to 1, what is J? J is equal to 1/2. What are the allowed values of M? M can be either, it starts at minus J, so minus 1/2. Then each time it increases by a increment of 1. So the next eigenvalue of M is 1/2 plus 1, which is what? Plus 1/2. That's it. So what are the associated eigenstates? These are the two eigenstates. Now you can also see one more thing, that in this case, you have two states, right? And again, you remember that these states will be orthogonal to each other because they are both eigenstates of Hermitian operators. So you remember that Hermitian operators have orthogonal eigenstates. So this you can think of as your spin down state, and this you can think of as your spin up state. So this is what we mean by spin up and spin down. Okay, this is why we call it down and up, because it refers to the eigenvalue of the LZ operator, right? So if LZ is equal to plus half, then if you want to represent that, right, as a vector, how would you write it as a vector? You would write it as a vector, and LZ is plus half. That means LZ is pointing in the same direction as L, right? Because in this case, they both have the same eigenvalue. So this is your up state. Similarly, if you have a down state, that corresponds to LZ is equal to minus half. Right? Then for n is equal to 2, what is the J? J is equal to 1. What are the allowed values of M? Minus 1, 0, comma, plus 1. So this is a spin 1 state. This J is called the spin of the state, right? What are the eigenstates? 1, comma, minus 1, 1, comma, 0, 1, comma, plus 1. Right? Now, if you want to draw this in terms of vectors, how will you represent this? You have This is your 1, 1 state. This is your 1, -1 state. And what about this state? This has 0 angular momentum in the z direction, right? So that means it must lie, this vector must lie in the xy plane. So since it lies in the xy plane, I can represent it like this. 1, 0. For n is equal to 3, j is equal to 3 halves, m is equal to -3 half, -1 half, +1 half, comma, +3 half. How should I represent this? Again, I will get this vector corresponds to 3 halves, comma 3 halves, and then I will have this vector corresponds to 3 halves, comma -3 half, and then I have two other vectors, +½ and -1, right? So the eigenvalue of L square is the same. That means the length of the vector remains the same, but the z component, the projection of this vector in the z direction, right? Okay, I'm trying to be a little precise here, right? So these vectors, they all have the same length. Okay, and then there is some angle here, let's say. So each time, so now you have 4 possible states, right? These are the 4 possible. But in this case, you don't have any Lz is equal to 0 state. All right. Same as here also. Here also you have no Lz is equal to 0 state. So these states, right? They correspond to what? We are talking about angular momentum. Now, where does angular momentum come into play? It comes into play when you have, let's say, something like a central force. So for instance, you have minus kq square by r square. You have a Coulomb force. This is the kind of force that you have, for instance, between a proton and an electron in a hydrogen atom, right? Now, if I write down the Schrodinger equation for this system, we will look at this Schrodinger equation in more detail later. For now, I will just write it down like this. Now the potential energy is minus kq squared by r, this whole thing times psi. And now we will write psi as a function of our polar coordinates, r theta phi, right? E times r theta phi. Okay, so now if you look at this equation, This equation has spherical symmetry. What does it mean for this equation to have spherical symmetry? This term doesn't depend on the angular variables. This term also doesn't depend on the angular variables, right? What about this term, the Laplacian del square? Now the Laplacian in spherical coordinates, it does depend on theta. But you can show that, so if you perform a rotation of your axis, right? If you perform a rotation of your XYZ axis, del square in the new coordinate system remains exactly the same as del square in the old coordinate system, right? So as an example, if you just look at del square, the Laplacian in your Cartesian coordinates, what is it? Del square is dou x square, dou y square, dou z square, right? Now let's say that I perform a translation of my coordinates, okay? So I have x, y, z, and let's say I translate my origin by some fixed amount, by some constant. So I take each point and I translate it by the fixed vector r, right? So x goes to x plus rx, y goes to y plus ry, z goes to z plus rz, right? What would happen to dx, dy, and dz? Dx would go to dx, dy would go to dy. There would be no change in this, right? These derivatives would remain the same because all I'm doing is shifting my origin by some amount. So in my old coordinates, I would write this as dx squared, dy squared, del z squared. In my new shifted coordinates, let's say I write Laplacian prime squared, what would it be? It would be del x prime squared plus del y prime squared plus del z prime squared. And this has the same form as the Laplacian in my old coordinates, right? So I would say that this Laplacian has translational symmetry. So just 1 second, let me just
What's her name?
her name is you don't need to know her name. Her name is Shiva. Okay. Say hi. 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 Everybody's understanding theory of angular momentum? Good. Now we're going to study group theory. Okay. Okay. Bye.
Bye, baby.
Shobham, you are very enthusiastic. Okay. So this del square has translational symmetry, right? Similarly, what we can see is that if I write del square in spherical coordinates, then we will find that it has rotational symmetry. If I write del square in spherical coordinates, oh, and by the way, this in Cartesian coordinates also you have rotational symmetry, okay? But in spherical coordinates, you have only rotational symmetry. You don't have translational symmetry. Because by definition in spherical coordinates, your origin is fixed. Okay. Okay. Now, do you remember that in earlier classes, long time back, we talked about the generator of translations. Does anybody remember what that generator was? What was the generator of translations? किसी को याद है?
Momentum.
कर सकता है? हाँ?
Momentum, sir.
Who is that? Sorry.
Vipul.
Vipul. Good, Vipul. This is your love for physics, right? Love is not just about words, it's about action. So generator of translations is momentum, right? How is this a generator of translations? If I take this momentum operator and I take exponent minus I delta x times p hat is a momentum operator, divided by h bar. And I take this and I apply it to any function of x. What do I get? I get f x plus delta x. And so this is the next exercise in your 6th homework set. Okay, you have to show this. So your 6th homework set will be due next Tuesday. And I think I've given you several exercises so far for this homework set. Right, this was one exercise. What else? Then this was another exercise. This had to do with time evolution and Heisenberg picture. Then this was another exercise. Okay. Right. So I've given you all these exercises. They are due on Tuesday. And as I told you in the last class that I won't be correcting all your homework sets. I will choose some of your homework sets to correct. So if you decide to play, what do you call it? If you think that, okay, well, maybe I'll submit homework 5 but not 6 because maybe homework 6 will not get corrected. You can do that, but then if I choose to correct homework 6, you will lose out on the marks for homework. Okay.
Yes, sir.
Okay, so this How will you prove this, by the way? Just to remind you, you will write P as this P as minus IH bar dx. So the exponent will become, you will get minus, you get plus. I think here I should put a plus. You will get, in the exponent, you will get something like delta x dou x. Now, this exponential, you expand this exponential in a Taylor series, and then you apply that Taylor series to f of x, and you get this. I mean, it's very simple, very straightforward. Okay. So this is what we mean when we say that momentum is the generator of translation. It is taking any function and it is shifting it by, it is translating it by the argument over here, delta x. So now you can apply this, by the way, not just for x, you can apply it for y, you can apply it for z. So in general, right, if you are in 2 dimensions or 3 dimensions, and you have some function of your coordinates, f of r, right? So r vector r can be either x, y, z, or it can be r theta phi. And you want to shift this function, you want to translate it by some amount delta r, right? So that corresponds to a translation of this form. So here maybe I'll put a delta over here. So I want to shift my everything by delta r. Then what will I do? I will have a generator. What will the generator look like? I think this is minus only. That generator will look like minus I. Now I will have one component in the x direction, one component in the y direction, one component in the z direction. So what will I get? I get vector delta r dotted with this momentum operator, but now this momentum operator is the momentum operator in 3 dimensions. So it's px plus py plus pz. So here also in this expression, I should write it as px, because it's only the component. Okay. And this I can write as minus IH bar gradient. Okay. So the momentum operator is the generator of translations, right? So where am I going with all this? Why am I talking about all this? What will be the generator of rotations? Any guesses?
Angular momentum, sir.
Right. So angular momentum, the angular momentum operator will be the generator of rotations. And we can see that. So now let me just show you from Sakurai, because that is faster than so in what way is angular momentum the generator of rotations? So that part actually comes before. So the order in which I've covered things is a little different from what Sakurai does, right? Sakurai talks about rotations before he talks about the eigenvalues and all. I have done it the other way around. So first of all, we want to understand what is a rotation. So rotation, right, is you take your vectors in your old basis, Vx, Vy, and Vz, and you apply some linear transformation to get your new vectors, right? Now, the thing is that, right, so this R is a matrix. Now, if you apply the inverse of this matrix, so you can easily show that the transpose of R will be equal to the inverse. So that tells you that R is going to be an orthogonal matrix. Now, what is one example of R? It is this matrix over here. What does this do? This performs a rotation around the z-axis. So if you multiply it by some x, y, z, you see that these two parts will act only on x and y, and this will leave z unchanged. Okay. So this is Rz. This will generate this generates rotations in the around the z-axis. Okay, a nice picture of that. Okay, that's too far ahead. Never mind. I'll come back to that. So now one can ask, what happens for very small values of phi? So if phi is approximately 0, so that will give you an infinitesimal rotation. So you ask, what is cosine phi for infinitesimal values of phi? You can use the Taylor expansion of this, which is what? 1 minus phi square by 2 plus phi to the 4th power for cosine. And for sine, what is it? It's just phi minus phi cubed, but then we ignore any powers of cubed and higher. Okay, so here he is writing R of z as a function of epsilon. Epsilon meaning it's a small parameter. So you get cosine, cosine minus sine and sine. Okay, this is R of z, and terms of order epsilon cubed and higher are ignored. Okay. Now one can ask, what is the rotation in the around the x-axis? That means in rotations in the yz plane, keeping the x coordinate fixed. Right? Well, those rotations will have the form, you will have the same matrix, but this matrix will now be in the yz over here. X will not change. You'll get cosine, cosine, minus sine and sine. Right? So you will get, if you look at R of x, you will get exactly the same thing. You'll get cosine, cosine, minus sine, sine, and this x part will remain unchanged. Same exact thing for Ry. The y part remains unchanged. The rotation is in the x of z plane. Right? Now one can ask, what happens if I multiply? What happens if I perform a rotation in the y around the y axis followed by a rotation around the x axis, or the other way around? Okay. Okay, never mind. I will stop here because apparently you all have a class, another class, classical mechanics class. So we'll continue next Tuesday. Okay. So thanks for sticking by. This
Thank
was
you, sir.
interesting, so I don't want to stop.
Thank you, sir.
But
Thank you,
we'll
sir.
continue next week. Yeah.